Could Mars have been habitable for much longer than we ever imagined? The answer might lie hidden in ancient sand dunes, now turned to stone, hinting at a prolonged wet period on the red planet. This challenges the established timeline of Mars's environmental decline and opens exciting new avenues in the search for extraterrestrial life. Let's dive in. For years, scientists have agreed on one key thing: Mars wasn't always the barren, desolate world we see today. Evidence overwhelmingly suggests that it once boasted a thicker atmosphere and abundant liquid water, creating potentially habitable conditions. We are talking about rivers carving their way across the landscape, lakes shimmering under a Martian sun, and perhaps even a global ocean. But here's where it gets controversial: the timeline of this habitable period has been a major point of debate. The prevailing theory paints a picture of a relatively short window of habitability, ending roughly 3.7 to 4.2 billion years ago. According to this model, the solar wind gradually stripped away Mars's atmosphere, causing its surface water to evaporate and disappear. However, recent findings are turning this narrative on its head, suggesting that Mars may have experienced intermittent or even continuous periods of habitability that extended far beyond this initial timeframe. NASA's Curiosity rover has been instrumental in this shift in perspective. As it diligently explores the Gale Crater, it's uncovering clues about Mars's past, piece by piece. And this is the part most people miss. It's not just about finding evidence of past water, it's about understanding how long that water persisted and what kind of environment it created. Now, let's zoom in on the latest research from scientists at NYU Abu Dhabi, NYU. Their groundbreaking study reveals that ancient sand dunes within the Gale Crater underwent a remarkable transformation billions of years ago. These dunes, over vast stretches of time, gradually solidified into rock through interaction with groundwater flowing beneath the surface. Their findings, published in the esteemed Journal of Geophysical Research, Planets, provide compelling evidence that Mars may have remained habitable for a significantly longer duration than previously believed. The research team, a collaborative effort led by Dimitra Atri, principal investigator of NYU's Center for Astrophysics and Space Science, CAS, and Vignesh Krishnamurthy, also from CAS, meticulously analyzed data gathered by Curiosity. They were joined by James Weston, Marie B. Elhandoui, and Professor Pants Naumov, bringing expertise from various NYU research centers. It's a testament to the power of interdisciplinary collaboration. Their focus was on the Stinson Formation, SF, a vast system of windblown sand and sedimentary rock within the Gale Crater. Curiosity's observations have repeatedly revealed evidence of these lithified formations, sediments that have hardened into stone. Given the extremely dry conditions prevalent in the Gale Crater today, the formation of these lithified dunes most likely occurred during the Noachian period, approximately 3.7 to 4.1 billion years ago, a time believed to be characterized by extensive flooding and rivers flowing into the crater. Think of it like concrete forming when water is mixed with sand and cement, but on a planetary scale and over eons. The team cleverly utilized the Mars Science Laboratories, MSL, Curiosity Notebook, a treasure trove of data collected by Curiosity's sophisticated instruments. To better understand the Martian landscape, they drew parallels with similar rock formations found in the arid environments of the United Arab Emirates, UAE, where water also played a key role in their formation. What they found was quite revealing. The team concluded that the Stinson Formation was the result of late-stage aqueous activity, meaning that these dunes were formed by interactions with groundwater from the surrounding mountains at a later stage than previously thought. This interaction left behind telltale minerals, such as gypsum, a soft sulfate mineral composed of calcium sulfate dihydrate, CaSO4, commonly found in Earth's deserts. What's even more intriguing is that this new research aligns with earlier findings presented by Krishnamurthy and Atri at the 10th International Conference on Mars. Their previous work focused on the Greenhill Pediments, GP, another dune formation with similar lithophyte rock deposits. Both studies point to the critical role of underground water systems in creating these unique geological features. But here's where it gets controversial. Could these water-rock interactions have also supported microbial life? On Earth, sandstone deposits hold some of the oldest evidence of life, including microbial communities that bind sediment and cause minerals to precipitate. These terrestrial analogues have led Etri and Krishnamurti's team to propose a captivating idea, that the lithophyte deposits in the Gale Crater might contain the preserved remains of ancient bacteria. Imagine discovering fossilized Martian microbes within these rocks. This latest research offers a new perspective on the evolution of Mars, shedding light on how it transitioned to its current state. It also suggests that the Gale Crater is an ideal location for future missions that will continue the search for life on Mars. These lithophyte dunes could be key to unlocking the secrets of Martian habitability. So, what do you think? Could Mars have sustained life for longer than we previously thought? And if so, what are the chances of finding evidence of that life within these ancient rock formations? Share your thoughts in the comments below.